right, let's talk about something we've all felt. That moment of frustration when your blazing fast 5G connection just dies the second you walk through a revolving door. Well, today we're breaking down a really clever paper called SpiderGNN that aims to solve this exact problem, using drones to essentially see 5G signals through walls. You know the feeling, right? You've got 5 bars of 5G on the sidewalk, but step into your office or apartment building and suddenly you're back in the dark ages. It's infuriating, but it's not just a personal annoyance, it's a massive engineering problem for every single network operator out there. And here's why it's such a huge deal. Get this. Over 80% of all mobile data traffic starts from inside a building. So if we can't get a good signal indoors, we're failing where it matters most. Cracking this indoor coverage nut is absolutely essential. So let's really dig into this indoor 5G challenge. The networks we have today are fantastic at blanketing wide open cities. But when it comes to punching a strong, reliable signal deep inside a concrete and steel skyscraper, well, that's a whole different ballgame. There are a few big villains in this story. First, those big cell towers on the ground, the macrocells, just weren't designed to push a signal up to the 30th floor. Then you have modern building materials, reinforced concrete, energy-efficient glass, which are like kryptonite for radio waves. They can kill a huge chunk of the signal. And on top of all that, you've got interference muddying the waters. Now, some folks had a cool idea. Why not fly a drone around the building to map out the signal? It's a great start, but there's one tiny problem. Drones can't see inside. And that brings us to the million-dollar question at the heart of this research. How in the world can we take those measurements from the outside and somehow use them to build a highly accurate picture of the signal on the inside? This is the massive puzzle that SpiderGNN sets out to solve. But to really appreciate how clever SpiderGNN is, we first need to understand the big mistake that pretty much all the previous attempts were making. It all boils down to one simple, fundamentally flawed assumption. So earlier models, like one called LADNN, were okay at predicting signal strength, or RSSI. Think of that as just the raw power. But they completely fell apart when trying to predict signal quality, or CQI, and that's the metric that actually determines if your video call is crystal clear or a pixelated mess. Why? Because they all fell into the same trap. They assumed that if 2 points are close in physical space, their signals must be similar. And this example just makes it so obvious. Let me paint you a picture. Imagine 2 spots just a few feet apart, but there's a thick concrete wall right between them. Geometrically, they're neighbors, but from a signal's point of view, they might as well be on different continents. Now, picture 2 spots 30 feet apart, but with a big glass window between them. They're physically distant, but the signal has a beautiful, clear path. It's clear that simple physical distance is the wrong way to think about this. It's just useless. And this is where the light bulb moment for SpiderGNN happens. The researchers said, okay, what if we stopped assuming we know how things are connected? What if, instead, we let the data itself tell us what the real connections are? This quote from the paper is just perfect. It's the entire philosophy in a nutshell. Instead of forcing a grid-like geometric assumption onto the problem, SpiderGNN decides to learn the building's true signal topology. It lets the radio waves themselves draw the map. So how does it actually do this? Well, the magic happens in a component they call the dynamic graph construction block. It looks at all the data points from the drone and uses an attention mechanism, which is a way for the model to weigh the importance of different inputs. It basically asks for every single point, which other points out there are your true signal soulmates, regardless of distance. Then it keeps only the strongest of those connections, creating this beautiful, sparse graph of how the signal actually propagates. Okay, so we've got this incredible, dynamically built graph that reflects reality. That's the foundation. Now let's look at how the rest of the SpiderGNN architecture builds on top of that foundation to make its final super accurate predictions. Here's the 30,000-foot view of the whole pipeline. Data comes in from the drone. It gets fed into that clever dynamic graph block we just talked about. Then, that smart graph goes into a topology-aware encoder, which is designed to think in terms of these new connections. And finally, the processed information gets split off to 2 specialized brains, one for predicting signal strength and one for signal quality. So think of the information flow like this. Step 1, throw away the old wrong map and let the data draw you a new correct one. That's the dynamic graph. Step 2, send out little messengers, in this case, a graph attention network, or GAT, to run along the paths of this new map, gathering intelligence and sharing it with their neighbors. They also use a trick called residual connections to make sure the messages don't get garbled and lose detail along the way. Finally, you have two expert decoders make their individual predictions, and you combine their wisdom for a final, stable answer. Now, having two separate predictors is another really smart move. The researchers realized that signal strength, RSSI, and signal quality, CQI, are just fundamentally different beasts. RSSI is kind of like the smooth, rolling bass line of a song. It changes slowly and predictably. But CQI is like the frantic, complex, and noisy hi-hat pattern. You can't use the same simple tool for both. So the CQI predictor needs a much more sophisticated dual attention design to capture all of its subtle, jittery behavior. Okay, the theory is elegant, the architecture makes sense, but does any of this actually hold up in the real world? Well, let's get to the results. And spoiler alert, they're not just good, they are absolutely decisive. And this is crucial. They didn't test this on some clean, perfect, simulated dataset. Nope. They went out and flew a real drone with real RF scanners around a real multi-story building in Sydney. They captured messy, noisy, complicated, real-world data. This was a true trial by fire. All right, brace yourselves because these numbers are just jaw-dropping. Let's look at the baseline, LADNN. For CQI, it's R-squared score, which tells you how well the predictions match reality, with 1.0 being a perfect crystal ball, is just 0.6. That's not great. Now look at SpiderGNN. Its error rate, the RMSE, drops by a staggering 89% for CQI, and its R-squared scores for both metrics are over 0.99. That's basically perfect. This isn't just an incremental improvement. This is a whole new level of performance. If a picture is worth 1,000 words, this one says it all. On the left, you see the predictions from the old baseline model. It's a shotgun blast of dots, a complete mess. That, my friends, is what failure looks like. Now, look at the right. That's SpiderGNN. It is a tight, focused laser beam right along the line of perfect prediction. That is what success looks like. And to prove that their dynamic graph was the real secret sauce, they ran what are called ablation studies. They basically took their brilliant model and deliberately broke it by swapping in one of those old, fixed geometric graphs. And what happened? The performance completely tanked. Case closed. The dynamic, learned topology is absolutely the key. So let's zoom out. What does this all really mean? This isn't just about one cool algorithm. This really represents a whole new paradigm, a new way of thinking about how we design and deploy wireless networks. I mean, think about the practical impact. First, it's non-intrusive. You don't have to send teams of engineers into a building for days on end to manually test every corner. Second, it's scalable. Got a new skyscraper going up? Just fly a drone around it for a few hours. And that means this is a practical tool that network operators can actually start using to make our connections better, right now. And the team isn't stopping here. The future roadmap is even more exciting. They're looking at supporting other frequencies, like the tricky new millimeter wave bands. They want to predict even more useful things, like latency and throughput. And the ultimate goal? To create fully autonomous drones that intelligently plan their own flight paths to gather the best possible data. So I'll leave you with this final thought. We are getting very close to a future where network planning isn't about reacting to problems and fixing dead spots after the fact. Instead, what if you could digitally model and perfect the wireless coverage for an entire skyscraper before a single person even steps inside? That's not just an improvement. That's a revolution for how we build our connected cities.